If p is a odd prime number and k is greater than equal to 1, then there exists a primitive root for p raised to power k. Proof by lemma 1 and lemma 2. Let us choose a primitive root r of p for which r raised to power p raised to power k minus 2 into p minus 1 is not congruent to 1 modulo p raised to power k. Thus, for any integer r satisfying the condition r raised to power p minus 1 does not congruent to 1 modulo p square will serve our purpose. In this way, such as r will be the primitive root for all powers of p. Now let n be the order of r modulo p raised to power k. Then by the theorem, let the integer have a order k modulo n. Then a is congruent to a raised to power k is congruent to 1 modulo n. If and only if k divides n h and n must divide. So phi p raised to power k is equal to p raised to power k minus 1 into p minus 1, since r raised to power n is congruent to 1 modulo p raised to power k, which implies r raised to power n is congruent to 1 modulo p. Again, by the above quoted theorem, p minus 1 divides n, so which implies n is equal to p raised to power m into p minus 1, where 0 is less than equal to m is less than equal to k minus 1. If n does not equal to p raised to power k minus 1 into p minus 1, then p raised to power k minus 2 into p minus 1 will be divisible by n. Then we get r raised to power p raised to power k minus 2 into p minus 1 is congruent to 1 modulo p raised to power k, which contradicts the choice of r. So therefore n is equal to p raised to power k minus 1 into p minus 1, and r is a primitive root of p raised to power k.